So where we finished yesterday, we were talking about tokens. So let me just quickly remind you of the token program, and I'll start by saying that this was written quite a long time ago. Uh, the idea behind tokens obviously is one that is very fundamental. So any blockchain is going to have some way of creating tokens. But this was written, the original token program was written a long time ago, and the way it approaches the particularly NFTs is very basic, as we shall see in a second. Fungible tokens, well, they are very basic anyway, but with NFTs, those kind of moved on, but we still had the token program doing them in a very basic way. Okay. But just to remind you, we have the token program, so that's where the functionality is. This is provided for us. We don't have to write our own code to do that. What we do need to do, though, is to set up the data for our particular token. So there's some of that data applies to all of the tokens that we are creating. So that's this mint account here. So that we saw the things that I've had in it. So things like the number of decimals, etc., and permissions around the token. And then when we are showing that somebody is holding tokens, then we also have an account set up for each person that has some of those tokens, and that will hold details such as the number of tokens they have, also details about delegation as well. Okay, so that's the how the accounts fit together for the token program. So we were going through the command line. This allows you to the token version, the SBL token CLI allows you to create tokens. And I talked through creating a fungible token. I think that was very straightforward. It's kind of doing very much what you would expect and allowing you to mint some tokens, check balances, etc., and transfer tokens. But I think I stopped before we went on to non-fungible tokens. And this is where the kind of the limitations of the program become perhaps a little bit more obvious, or the the simplicity really of the approach it has taken, because it does allow you to create an NFT, but it does that in a very particular way. What you do to create an NFT is you create a token, but you make sure that it has 0 decimal places, which well, that's I guess kind of standard, but there are times maybe you'd want an NFT to have decimal places. You can have more complex ideas, but for this, in this one, we're setting the decimals as 0. We need to set up the account as before, for as we did with a fungible token. What you do then is you mint 1 token to that account, and then you disable future minting. So this is a way of creating a token that we know is going to be non-fungible because it's not possible to create any more tokens of that type. So it's unique. It has an identity because it's the only instance of that token. Um, but as you can see, we've kind of restricted what we've done. We've sort of started with the idea of a fungible token, and then kind of clamped down, restricted the details of that to give ourselves a non-fungible token. But you can do that, and you can check the details about that as well as before. Now, obviously, I mean, maybe when these things were first created, maybe that was sufficient for people. But the way that people use NFTs now is much more sophisticated than this. And so what has happened is that tools have been created to provide the sophistication and the functionality around NFTs that we really expect. Because having something like this is not sufficient, really. We want to be able to create collections, and we want to be able to have auctions and have marketplaces and all sorts of things like that. And we want to link this to digital assets, and yeah, uh, that's not being provided for here. So, but this is the way that we can create a non-fungible token, the most basic way that we can do that. Okay, but we're going to talk about all these tools and the extra things that have been added in a short while. Okay. Now, before I do that, sorry, I need to go. Sorry, go back. Uh, I just want to talk a little bit more about programs. I'm going to not talk too long today. We're going to go into breakout rooms shortly, but I just want to cover a few points about programs and PDAs. So we've covered a lot about programs, and we've talked a lot about the details of how they work, the entry point into a program, etc., and all that kind of thing. So there's a few other things we need to know. One is about the compute budget, and this is a way to limit the amount of computation that can be done. Otherwise, then we could get things being abused. We could get denial of service attacks happening if you didn't have some way of limiting the amount of computation that can be done by an instruction. So we have this idea of the budget, the number of computation units that are allowed, and then these are used up as the program executes. And then if you go through the budget, then the program will halt and you'll get an error. Um, the usual things count as computation, so executing instructions, doing system calls, what you would expect, really. Um, So the because of that, it does mean that there is pressure on us to make our programs efficient, which is no bad thing. So you do have to think about making sure that your programs are efficient. They're going to compute with as few resources as possible because you're asking a blockchain, you're asking a lot of nodes to do this computation. So it's good that you are thinking about that. Um, yeah, so if it runs out, you will get some errors that look like this. Um, you also have limits as well on the amount of memory that can be used. So not just the number of instructions that you're doing effectively, or the amount of computation, but the amount of memory and the amount of stack that is needed. So that is also something that is restricted because again, it could there's potential there for abuse if someone tries to use too much memory, create huge objects. So you also have to be a little bit careful about that. So the takeaway is make sure your programs are, quite efficient in terms of the algorithms that they're doing, and that you don't uh, create large objects that you don't really need. Yeah, and also recursion. Yeah, so you need to be a little bit careful about the depth of that as well. If you want to know how much compute budget you have, then there's a system call that you can use to log that. So you can check that if you're worried about that. Uh, the next part, I've really explained this already, I think. So I don't know if I need to go through this again. It's just to say that over time you'll probably want to break up your program into modules, and we've seen what those look like generally. Okay. So I want to quickly then talk about program-derived addresses, PDAs, because this is a big topic. It's adding complexity to the way that we use accounts, but there's good reasons for that. There is motivation behind that. We do need this solution, but it is something you're going to need to be comfortable with because you are going to need to use these solutions. Um, So, as background, remember the state that we are going to update by our program needs to be passed into the program. Uh, the program can only alter the state of accounts that it owns, um, but it can alter any data within that account. But then, if you're thinking about that program sending an account to another program, we have a problem because it cannot sign for it. So what PDAs try to do is to try to solve this problem so that programs can communicate with each other, can uh, and send accounts to each other, but to do this in a secure way. Um, So there are checks around the accounts and who is allowed to sign for them that is going on. Obviously, we need that. We need to make sure that accounts that are going to be updated do have some signature involved with that is allowed. Um, but of course, if you're doing the signing off chain, if the client is doing the signing, that's okay. The client has their private key. But you can't do that on chain. You can't do the signing on chain because we can't have a key on chain. So that's a basic problem. So the way we get around that is to have a special mechanism within the runtime which allows a program to sign for an account, but without having a private key. But in order to do that, we need special types of accounts and special types of addresses. So that's what a PDA is all about. It is allowing this mechanism so that programs can sign for a particular account. And the PDA, the program derived address, is absolutely bound up with the program that is going to be using that. So it's not the case that then this it could be created, a particular PDA is created for any program. It is for a specific program. And it allows us then to do this cross-program invocation. So it allows us to communicate with other programs and sign for accounts going into other programs. So there are special types of addresses. So the accounts that are going to be used have a special type of address. They look like a normal address, but the important point is that they don't have a private key, and that's important because we've got this special mechanism to say we're going to make an exception. We know this can't be signed for by a user, so we're making a special exception. But and so it's only a program can do that. A particular program will be able to do that. So we don't want then someone to actually have a private key for that address and to be able to sign for it because it should be controlled by the program. So I'll explain how we can be sure that it doesn't have a private key. I'll explain in a second. When you want an address of these one of these special addresses, there's a way to get one. We often talk about finding them really rather than creating them, but it is derived from certain details. And the first thing it is derived from is the program ID. So that's how it is tied to a particular program. Uh, then it is. We also have this idea of what is called a seed. It's just a collection of bytes. And the reason we have that is that if we didn't have that, if we just derived this special address from a program, that would mean that that program could only ever derive one address, which we probably don't want that. We probably want that program to be able to derive many addresses. So in order to do that, then we derive it from the program ID and a seed, a collection of bytes. And then we have this extra thing called a bump, which I'll explain how that works in a second. But when you've got those details, it is a deterministic process. So with those details, you can derive the address of one of these special accounts. Okay. And when you've got that, and if you create an account with this address, then that can be used for cross-program invocation by a program. But as I said, it's tied down to a particular program. Each one of these special addresses it belongs to a particular program. So that's why we have it being derived from the program ID, and that will be checked when you try to do the cross-program invocation. There will be a check to make sure that that has come from the correct program. Okay. I'm sorry, I can't remember what I wanted to say about this indexing. I'll come back to that. So why would we want to do this? Well, there are many use cases where we need this type of functionality. So we've got examples here where somebody's playing a game, but they need a kind of an escrow account to be holding funds for the two users playing the game. Um, but we don't really trust either of the users to be in having an admin to have an admin function to uh, to resolve the uh, sending out the funds. So we need this special escrow role. And then that is something that can be done by a program. But in order to do that, it needs to use uh, these special accounts. It needs to be able to sign. Okay. Other things, also things like auctions as well, that will be transferring assets, or anything that's distributing prizes. So a lot of use cases. There's a lot of reasons why we want this functionality. Um, yeah, I've just said that as well. So, um, oh, and this is the a diagram just to show what the escrow would be like. So to say really, this is not being, it's not the users that are signing for the transaction when we are transferring the funds, because obviously there could be cheating going on, or somebody could refuse to sign, all that kind of thing. But we can get the PDA to do that. Okay, so how do we actually get these? And particularly, how do we know that there's no private key for this particular address? So if you think back to what we were talking about last week, where we talked about elliptic curves and the points on an elliptic curve, and the fact that we can start with one of those points and do an operation, and then that will give us another point on the curve. And the cryptography we do relies upon that, so that the addresses that we have are public keys, are going to be points on this curve. So what we do to when we create one of these special addresses is that we start with uh, we start with a point that is on the curve, and then we use this bump that I mentioned earlier to move the point off the curve. And what the reason that we do that, and then that can be used as an address, is because we know that this could not have been reached by our usual types of operations. Because any type of operation that we would do on elliptic curve points will always produce a point on the curve. So if we take a point and then move it off the curve, we know that then that is unreachable by any of our normal cryptographic operations. So there's no private key that could go through the normal derivation process of private key to public key that would actually get a public key that is off the curve, because every time we do those operations, we end up with a point on the curve. Okay. So that's how we're confident, how we know that our PDA doesn't have a private key. Okay. Um, so in order to get them, yeah, we have we call this uh, the find program address, and we pass in seeds and the program ID, and then we need to do the bump as well. So all of that will then give us one of these addresses. Okay. Now this does introduce a slight problem uh, because of the way that the runtime works. If you remember, I said that as transactions come into the network, the runtime is trying to do things, look at what can be done in parallel. So it needs all of the information about the accounts that are going to be used, and about the are going to be used by the instructions. So it needs to know everything, really, the runtime. So what it needs is, if there is going to be a PDA being used, then it needs to know about that. It needs to know what that address is, so that it can do all of its checks to make sure that it can do some processing in parallel. So uh, in order to do that, we need from the client, if we're going to be using a PDA that hasn't been created yet, um, the client needs to work out that address. It needs to derive that address, so that the runtime will have that information. Even though we may be doing that derivation, uh, within the program. So that may be being done on chain, and we're expecting to do it on chain. If that's going to be used in a transaction, then the client also has to do this. It also has to work out what that particular address is going to be. But that's okay because we can do that. It's a completely um, we can derive that. It's completely deterministic, and so the client can then use the program ID, use the seeds and the bump, and from that it can work out what address is going to be used, even if that hasn't been created yet. Even if we're actually going to do that in our program, and our program is going to do the derivation again, and then ask the system program to create an account with that address. So that's just a little extra thing that we need to be aware of when you're writing your client and you're interacting. If you're going to use PDAs, then that you may have to do that as well. Okay. Um, so they are a little more complex, but you'll still get used to them. You'll see. We'll go through some patterns, and we'll give you some examples about to show you how they're used, and yeah, you'll get the hang of it. But that's it for today. I hope you enjoyed that. I hope you all have a good evening, and I look forward to seeing you tomorrow. Bye bye.